So here's the setup of our system. As usual, we have a laser going into a spatial filter, and then that goes into the shack cube, which has a beam splitter. There's a convex lens here that sends the beam over to this mirror, which goes back through the convex lens and focuses somewhere around here. The other pass through the beam splitter just goes through this lens. So we aligned the two focus points from the mirror route and this lens route so that the wavefronts in an ideal imaging system would be about the same, and any aberrations in the system then will cause slight differences in the wavefronts here, which will show up as an interference pattern back here.
What makes a shack cube different from a regular beam splitting cube is its curved surface, which is the highest precision surface required for this setup. We see interference fringes because the reflection from the curved surface, shown in blue, and the reflection from the test mirror, shown in green, are made to come into focus at the same spot, slightly behind the cube, and then imaged onto graph paper for viewing. We notice that when the numerical aperture of these two cones coming to focus are similar, the setup is much more easily aligned than when the NAs were different. In this lab, the short focal length mirror was easier to set up. Since the reflection off the curved surface had a much lower intensity than the reflection off the mirror, we tried to attenuate some of the light going to the mirror in order to make the fringe contrast better. We did this by putting a polarizer here and rotating it through a full semicircle of angles to find an angle that would give the best contrast. The shack cube interferometer works differently than the shear plate interferometer in that it interferes two spherical waves instead of two plane waves, similar to a Young's double hole experiment. So we see interference fringes that look like this.
Here we've attempted to null out the fringes from our test mirror, and we can just see about 2 rings left, so there might be a little bit of defocus left. Here we are at the null fringe for the shorter focal length mirror, and we see about 1 or 2 fringes left in there, and if we defocus it, then we can add as many fringes as we want.
This interferogram shows defocus and tilt. The position of the fringes is due to the tilt, and the circle are due to the defocus. These circular fringes show that the lens is defocused. As you can see here, there's mostly straight line fringes, which means that a lot of the defocus is gone, and the position of the fringes has tilted, or has translated horizontally, which shows that there's tilt in the system.
The post-processing of the data is going to be very similar to last week. We'll take a cut across the x-axis and fit the fringe order to its location. For a fourth order polynomial, we'll be looking for spherical, defocus, astigmatism, coma, and tilt. But since there isn't just one shear direction in this experiment, we'll also take a cut along the y-axis and fit those fringe orders to their location. And then we can utilize some equations to find the wavefront error coefficients.